Welcome to AP Podcast 14.9. We are continuing on our acid-base property journey, and what we're going to do now is look at the fact that the structure actually plays a role. Just when you thought you knew everything about acid and bases, here comes something else. Well, a couple things that we need to be reviewing. We know that any molecule with an H in it has the potential to do this, right? So that's just something to be aware of. But there are a bunch of things with H in it that are not acidic. Okay, for example, let's imagine something like a methane, CH4. All right, that's not an acidic molecule. It won't be acidic when you put it in water. And one of the reasons why is that the stronger the bond, the less acidic. Okay, so this is a pretty strong bond between H and C. But the other thing that's important, because if you can imagine things like this, HF, right, and HCl, the other thing that's important that plays a big role is how polar it is. The more polar, the stronger the acid, all right? And so if you look at something like the difference between HF and HCl, this is going to be more polar, right? But which one do we consider the stronger acid? Well, this is the stronger acid. So in water, it turns out that even though this is more polar, this is going to be a stronger acid. So just some things to think about. It's the polarity that's involved and how strong the bond is. Another thing that we have to deal with is this thing right here. Okay, when we have oxyacids, the more polar the bond there, the stronger the acid. And I've got some diagrams that'll show that for you. So let's look at these oxyacids real quick. The more oxygen is hooked to the central atom, the more acidic the hydrogen. You guys know that the seven strong acids, and Hicolo is definitely part of it, but it's only these two right here. These two are considered strong acids. These two are considered weak acids. And the reason for that is the way that the charge density on the molecule plays a big role in how polar that H is. The H is attached to an oxygen atom. So if I'm looking at something like HClO2, we've got Cl, we've got an O there, an O there, an O, pardon me. And one of the H's is attached right there. Okay, that's not a very good drawing. In fact, my organic chemistry professor would probably shoot me if he saw that. But anyways, let's draw it like that. That's a little better. So the fact that this H is attached to the oxygen right there is going to determine on how acidic this molecule is. Oxygens are more electronegative, and they're going to pull away from this bond right here. So let me show you a diagram I have. This is right out of your book. So we've got, notice this says electron density. You can't really see it there, but that does say density. Okay, so the electron density, in other words, if you were to imagine drawing some clouds, it would be heavy here and then kind of small here. Okay, now if we go to the next oxyacid, we've got this situation. Again, the density is getting bigger. And over here, the density is getting even more so. And with the last one, the perchloric acid, it's even greater. So what that's doing is because we are so polar on this side, okay, this side becomes much more electropositive, whether it's that one or this one. Same kind of situation. More electronegative on this side, more electropositive on this side. And so with those two situations, what that does is that allows this area right here to be an area of weakness, and that allows the H to disassociate and form a hydronium ion. And so when you get something like this, where the charge density is not that great, it doesn't come off quite as easy. Same with the ClOH. Okay, so those structures do play a big role in whether or not the acid is strong or weak. So when we talk about those seven strong acids, the polarity plays a big role in whether or not it's a strong acid. All right. Now let's look at one more situation, and that's where we have something like, remember I mentioned more about later, let's imagine we have something like aluminum floating around. Aluminum is very polar on the positive end, right? And what's it going to attract? It's going to attract the oxygen. Well, this is a very similar situation to what we have right here. All right, we have such a greater charge on this side that it makes the bond right here, and makes it easier for H to come off and make an H plus. Right? And so where you have to really look for this situation is when you're talking about highly charged metals. Aluminum is typically the example they give. Not so much with a metal that's got a positive 2 charge, but it still does happen. So that's something we need to be aware of, is that metals that get hydrated tend to form acids. And it's because of this charge density. All right? And then last but not least, I want to finish this podcast with this situation, because this is something of a review for us, but it is still important, and that is what happens when you dump some of these molecules in water. Well, if it happens to be a non-metallic oxide, all right, and that's like sulfite right there, pardon me, sulfur trioxide, it makes sulfuric acid, all right? And you can see that with, let's imagine we had SO4. Sulfur, oops, pardon me, let me do this again. How about SO2? SO2. SO2 tends to make H2, oops, SO3, all right? So those things happen with non-metallic oxides. So imagine me dumping in some NO2 into water. Again, what would you make? You would make nitric acid. Okay? So there you have it. Now on the other end, if you have a metallic oxide, metallic oxides dissolved in water always produce a base. Now when I say always, I want to focus mostly on the group 1 metals, and group 2 metals. All right? Because that's the examples we're going to see all the time. So those are just two of the things that cause bases to form. All right, so there you have it. Structure is important. Bond strength is also important. And then really it comes down to the electronegativity, I say, is probably the most important thing. So there you have it, and we'll see you next time.